right, so in the last part, we derived this formula for computing the work done by a force moving an object from point A to point B along the x-axis. And it ended up looking like a definite integral. So now what we need to do is work through some different types of examples where we have to compute the work done by a force. We're going to start with the simplest possible case where I just give you the function that you need to integrate and we do a direct integral. So here it says an object is located x feet from the origin and a force of 4 times quantity x cubed minus x pounds acts on it. Determine the work done moving the object from x equals 2 to x equals 4. Okay, I could draw a diagram for this one, but this one is so straightforward that there's not a whole lot to really concern ourselves with as far as a picture goes. I'm just going to go directly from my reading of it. Okay, so we're given our force right here. This is our f of x. And notice that we're in imperial units because it mentions pounds right there. Okay, so that's going to tell us the units that we're going to use once we have an answer to measure our units of work. To determine the work done moving from x equals 2 to x equals 4, this is like the a and the b in the derivation that we came up with in the previous video. So to compute that work, I want to set up a definite integral where my limits of integration are 2 and 4. Okay? The function that I'm integrating is this one. I'm going to distribute that 4 in because I'm going to find that in this case it makes my integration a little bit easier. 4x cubed minus 4x dx. Okay, so all I did is I used our formulation here, or our work integral, directly. And now it's just a matter of computing it. This is a simple integral to work out. I'm going to get x to the 4th minus 2x squared from 2 to 4. Okay, and then computing that is straightforward. Plug a 4 in. 4 to the 4th power is 256 minus 4 squared is 16 times 2 would be 32 minus, remember to put parentheses around the second part. That's the mistake most people are going to make at this stage in a problem like this. Don't forget those parentheses. Plugging a 2 in, 2 to the 4th power is 16. 2 squared times another 2 would be 8, so this becomes minus 8 right here. At that step, it's just straightforward arithmetic. What did I work that out to be? 216. And because we're working in imperial units, this would be measured in foot-pounds. Foot-pounds. Not newtons in this, or not joules in this case. Okay? So that's super straightforward. It's a direct application of that integral. We're going to see in the remaining examples, I think we have 3 more examples that we need to get through. The process involves a few more steps than just doing this, depending on how the problem is framed. So for the next example, before we can get into that, we need to talk about something in physics known as Hooke's law. Hooke's law concerns springs. Specifically, what it says is that the force required to keep a spring stretched x units beyond its natural length is directly proportional to x. Or we can represent that as a function this way. F of x is equal to k times x, where k is some constant. So when we use the term natural length here, what that means is if you had a spring and you didn't apply any force on it at all, its length is that natural length. When you apply a force on a spring, that can either compress or extend that spring beyond its natural length. Okay, this k here, this constant in physics, we call that the spring constant, and it depends on the spring that you're using. Different springs will have different spring constants. Okay, so let's take a look at an example where we want to compute the work done where a spring is involved. So if the force needed to stretch a spring 1 foot beyond its natural length is 12 foot-pounds, how much work is needed to stretch it 9 inches beyond its natural length? So for this, I like to draw a little diagram here. For this, let's assume that this is the natural length of the spring. So notice I have pulled this string down and extended it beyond its natural length. I'm going to think of its natural length as, 0 here, okay? And if I want to pull it x units beyond its natural length, then I would think of this as x down here. So going from 0 to x gives me a total of x units beyond the natural length of that spring, okay? So x does not represent this total length, it represents this total length here. All right, what information do we have? Well, first of all, we have Hooke's law. Hooke's law says that the force required to stretch a spring x units beyond its natural length, here's x, is equal to some spring constant, which we don't know yet, times x. Notice the problem never tells me anywhere k equals this, or the spring constant equals this. We have to figure out k before we can really go any further. So let's see. I am told that the force needed to stretch the spring 1 foot beyond its natural length, that's x, is 12 foot-pounds. So in this case, the force is 12 foot-pounds. And that's equal to k times the distance beyond the natural length that we stretched the spring, in this case 1 foot. Now I want to keep that as 1 foot. I don't want to convert it to 12 inches or something similar because my units of work need to be foot-pounds. So my units of length or distance need to be measured in feet only and not some smaller or larger denomination. I can see that this would imply that k is equal to 12. So now I have a more explicit function. The f of x that I'm using here is 12x. My first step was to figure out k so that I could rewrite this function with that constant known. Okay, what is the next thing that I need to do? Well, now it says how much work is needed to stretch this spring 9 inches beyond its natural length. So to determine that, I'm going to have to think about this x being 9 inches. Now it's work. We know that work is equal to an integral, and to stretch this spring 9 inches beyond its natural length, I would be starting at its natural length, which I'm thinking of as 0, and stretching it down to that 9 inches. So the upper limit of integration here should be that 9 inches, but I actually don't want to write 9 here, because that's the wrong units of measure, inches. Everything should be interpreted as feet when I'm talking about distances here. So instead of saying 9 inches, I want to call it 0.75, because 9 inches is 3/4 of a foot, or 0.75 feet. Okay, then I want to insert my function as my integrand, 12x, that's the force function, dx. Okay, this is a super straightforward integral. I get 6x squared from 0 to 0.75. Obviously, plugging a 0 into this gives me a 0, so really I just need to do 6 times 0.75 squared to get my answer. 6 times 0.75 squared. Work that out by hand or with a calculator. This one will come out to 3.375 joules. Oh, no, I'm sorry. We're not measuring this in joules. We're doing this in foot-pounds. So foot-pounds. Be careful with my units. Okay? And again, not super complicated, but we did have this additional step of having to figure out what f of x looked like in the first place. All right? So that's one more example under our belts. Let's move on to something different. Okay, this one will not use Hooke's law because there's no spring involved. It says a thick cable, 60 feet long and weighing 180 pounds, hangs from a winch on a crane. Compute the work done winding up 25 feet of this cable. So this, I'd like a diagram for this. I'm going to think of this as my crane right here. And I have this cable that's hanging off of that crane, okay? And this little winch here is going to wind up part of that cable. For this, and you're going to see this is the case for most work problems, we want to create a coordinate system that suits this problem. And for this particular problem, it's helpful to use a coordinate system that's inverted. And what I mean by that is I'm going to put the origin here, and I'm going to think of down as the positive direction. You can do this without inverting your coordinate system, but it ends up making the work just a little more complicated. So choosing a coordinate system intelligently can help take a lot of the difficulty out of a problem. Okay, now as I go from here down to here, this is the end of my cable, and we're told that our cable is 60 feet long. So I'm going to think of this as 60 right here. Okay. Now I need to think of this kind of in two parts. So we're only winding up 25 feet of cable, right? So 25, let's see, this would be about 30. So I'm going to say 25 is like right here, right? So this part of the cable is going to get wound up. And this part of the cable is going to move up with it, but no part of this cable is actually going to get wound into the winch. And the reason that's important is because parts of this cable, like say for example, in fact, let me do this. This is how we're going to solve the problem. I'm going to take this first 25 feet of cable and partition it up into little subintervals, kind of like we did when we derived our work formula. And I'm not going to draw them all. I'm just going to draw one of them. Let's suppose this one right here. Okay. So I'm going to think of that as like xi minus 1 and xi. And let's denote the width of that thing by delta x. Okay. And then again, just like we do for the derivation of a work problem, I'd like to pick a single sample point in there, which I'm going to call xi star, like that. Okay. Now, let's think about how we would compute the work done winding this little piece of our cable up. Okay. The first thing I need to do is determine what the force on this little segment of our cable is. Remember, when we're working in imperial units, force is the same thing as weight, at least for this type of a problem. So when I'm saying pounds, that's a measure of force. So the first thing I want to do is figure out this little subinterval right here. How much does that little piece of our cable weigh? Well, the first thing I need to do is figure out how to relate the 180 pounds total of this cable to the length of that cable. I know that the cable weighs 180 pounds, and the cable has a length of 60 feet. If we assume that the weight of the cable is evenly distributed, meaning parts of the cable are not heavier than other parts of the same length, then 180 pounds divided by 60 feet will give me 3 pounds of cable per foot. So it's a rate, right? It's a rate of weight per foot of cable. Now, if I'm looking at a little subinterval whose length is delta x feet, I can find the weight of that, which again, that would be force. I'm going to call it Fi because it's going to represent the force on just the ith subinterval here. It would be equal to this 3 pounds per foot times the length of cable there, which is delta x. So that is the force acting on this piece of cable right here. Next thing I need to do is multiply that by the distance that is going to move. Okay. Now this has to overcome gravity, so we're applying this force, but in this direction, and it needs to move a distance of about xi star. Now the reason I'm saying about xi star is because xi star is how far this exact point within that subinterval is going to be wound up. Other points within the subinterval might be moving might be lifted slightly more or slightly less, but because I'm going to think of this as a very small subinterval, I'm going to approximate the distance of each of these points, the distance at which they are wound up by this winch, by just using xi star for all of them. Okay, so the work done lifting this little segment of cable, the subinterval of cable, is equal to the force, 3 delta x, times the distance, which I'm thinking of as xi star. Or I could write that this way, 3xi star delta x, okay? Now, That thing is, I can apply this to all of the little sub intervals that I would cut this guy into. And actually, I meant to just go from down to here because we're dealing with this cable in these two separate parts here. But the way that I want to compute the total work done is approximate the work done on this part of the cable by summing up all of these for each of the subintervals. So the total work done is approximately this summation, the sum as I goes from 1 to n, assuming there's n subintervals here, of this function, 3xi star delta x. And I can get an exact answer out of this if I let n go to infinity. So the work done, and let me actually call this W1. I want to call it W1 because W1 is going to represent the work done lifting this part of the cable, and then in a separate step I need to think about the work done on this part of the cable. I'll call that W2. But this would equal the limit as n goes to infinity of this summation, because remember what that's doing is it's making those subintervals smaller and smaller, which gives me greater and greater accuracy. Okay, this limit turns that Riemann sum into an integral. And this time, what are the limits of integration on my integral? Well, looking at my coordinate system, I have a cable going from 0 all the way down to 25. So 0 to 25 is my are my limits of integration. This becomes a 3x. Delta x becomes dx. Integrating this gives me 3/2. Actually, I don't need this little square bracket this time. 3/2 x squared from 0 to 25. I am going to skip doing all of the work for this because at this point it's arithmetic and you should have a good handle on that by now. This comes out to 937.5. And again, we're working in imperial units, so we want foot-pounds. Okay, now we're not done because I need to consider the work done on this part of the cable as well, because this is hanging off of this thing. It requires work to lift all of that with these 25 feet of cable here. But this actually is a simpler computation. You can do this with an integral, but you can also avoid using an integral if you keep in mind that for this segment of cable, it's a constant force that's going to be applied, lifting it all the way up here. It's not a constant force for these 25 feet because this segment of cable is getting shorter and shorter as it gets wound up. So it's less and less weight on that little segment the entire time it's being wound up. But this segment never makes it to the point where it gets wound up in that winch. So that's going to be a constant weight the entire time. And remember, weight is force in imperial units. So what is the weight of this piece of cable? Well, first of all, it's going from the 25-foot mark to the 60-foot mark. 60 minus 25 is 35 feet. That means that we have 35 feet of cable here, and the cable weighs 3 pounds per feet. So 3 pounds times 3 pounds per foot times 35 feet is equal to 105 pounds worth of cable. And that 105 pounds is not changing because it never gets wound up. I was off the screen there for a second. Now, because this is a constant force, I can just use the original formula that we had for work that didn't involve a definite integral at all, which is force times distance. Okay, the force is 105 feet. What is the distance? Well, this entire piece of cable is moving a total of 25 feet from this position up to this position. So that's going to be what I multiply by, 25 feet. Okay, 105 times 25 is 2,625. So 2,625 foot-pounds. Okay, now I need the combined work. I need the total work done lifting this cable, which is just W1 plus W2. The total work done is 937.5 plus 2625, and that's equal to 3,562.5 foot-pounds. Okay, that would give me the total work done lifting the entire cable. Notice that for this one, we had to kind of think of the problem by setting up a Riemann integral. We didn't just jump straight to a definite integral. We actually set up the Riemann sum first and then converted it to an integral, because that's actually the easiest way to approach these types of problems. It's also how we're going to approach the next example, but we're going to save that for the last part.